Ever stop and think about the invisible systems that are basically the traffic cops of the internet? Well, today we're going to pull back the curtain on the rules that stop our digital world from becoming a total chaotic mess. Let's dive in.
I mean, it really feels like magic, doesn't it? You've got a movie streaming, a huge game is downloading, and your emails are still popping in, perfectly fine. How on earth does your computer know what data goes where? That's the exact mystery we're solving today.
So, to really get this, let's imagine the internet as this gigantic, unbelievably efficient post office. This whole system is built to take every single thing you do online and wrap it up into a perfectly deliverable package. And here's where we're going to be spending our time: the transport layer. This is the absolute key, the bridge between the apps you're using on your screen and the network that's actually sending all the information. You can think of it as the main sorting facility for our entire digital post office.
Okay, so how does it handle something huge like a 4K movie? Well, it doesn't just try to shove the whole thing down the pipe at once. No way. It uses this really clever trick called segmentation. Imagine you're trying to mail a 1,000-page book. You wouldn't send it as one massive clumsy brick, right? Of course not. You'd send it page by numbered page. That's exactly what segmentation is, chopping up big messages into smaller, numbered pieces called segments.
Right, so the data is chopped up and numbered, but how does your computer know that these segments are for Netflix and those are for your email client? That's where port numbers come in. Think of your computer's IP address like the street address for an apartment building. The port number, that's the specific apartment number. It tells the package exactly which door to go to. And this isn't just random guesswork. There are standardized, well-known ports for all the common stuff we do. You can see right here, port 80 is the universal address for web traffic, and port 25 is for sending email. This whole system keeps that flood of data totally organized, making sure your movie doesn't end up in your inbox.
So now our data is all packaged up and addressed. Our digital post office now has a big choice to make. Does this package need to be sent with 100% guaranteed reliability, or does it need to get there as fast as humanly or digitally possible? Because you can't always have both. And that brings us to the two main delivery services, TCP and UDP. TCP, that's the Transmission Control Protocol, is just like sending something by certified mail. It is meticulous, it tracks every single piece, makes sure it all arrives in the right order, and it even asks for a signature, an acknowledgement, for everything it delivers. Then you've got UDP, the User Datagram Protocol. It's the total opposite. It's like a postcard. You just scribble a note and drop it in the mailbox. It's ridiculously fast with almost no overhead, but there's zero guarantee it'll ever get there. This table here really lays out the trade-offs perfectly. You see, TCP is connection-oriented. It guarantees reliability. That's why it's perfect for things like downloading files or browsing websites, where every single bit of data has to be absolutely perfect. But UDP, why would you ever use the postcard method? Well, think about video streaming or online gaming. Speed is everything. Who cares if a single pixel is off for a millisecond? It's way better than pausing the entire stream just to wait for one lost packet to show up.
Let's zoom in on our certified mail option, TCP. When you look at its shipping label, which is called the header, it looks, wow, incredibly complicated. And yeah, it is. But don't worry, we only need to get a few key parts to understand how it pulls off that guaranteed delivery.
It really just boils down to this. First, you've got your source and destination ports. Those are our to and from apartment numbers. Easy enough. Then you've got the sequence and acknowledgement numbers. These are the supercritical page numbers that let the receiver put the book back together in the right order and tell the sender, yep, I got page 42. And finally, there's a checksum. Think of it like a special stamp that proves the package wasn't opened or damaged on its journey.
So we have our delivery methods. We're good to go. But what happens when the digital highways get totally clogged? You know, when everyone tries to send their data at the exact same moment and you get a massive digital traffic jam? Well, one of the most clever solutions is a traffic shaping algorithm called the leaky bucket. Its whole job is to take unpredictable, bursty traffic and smooth it all out into a nice, predictable, constant stream. And this image explains the concept perfectly. Just imagine data packets are water. You can pour them into this bucket in huge, sudden bursts or as a slow little trickle. It doesn't matter one bit how they go in. They can only leak out of that little hole in the bottom at one steady, constant rate. The logic is really simple and really strict. Packets arrive, they go into a queue, that's our bucket. The network then pulls packets out of that queue at a fixed rate. But here's the catch. If a huge burst of traffic comes in and the bucket is already full,
Any new packets are just dropped. Poof, they're gone. It's rigid, for sure, but it does protect the network from getting totally overwhelmed. But what if you need more flexibility? What if rigid just won't cut it? Well, that's where a much more adaptable system comes into play, the token bucket algorithm.
Now, with this method, instead of managing the data packets themselves, the algorithm manages tokens. You can think of them as permission slips for sending data. These tokens are added to the bucket at a steady rate, and to send anything, a computer has to grab a token and spend it. So here's how it works. The bucket is just constantly filling up with these tokens. When you want to send a packet, you check the bucket. Got enough tokens? Great. You take them out and send your data. If there aren't any tokens, your packet has to wait. Now, here's the really genius part. If the network is quiet and you're not sending anything, those tokens just build up. You save them. Then you can spend all those saved up tokens at once to send a huge burst of data, giving you this awesome speed boost right when you need it. So which one's better? Well, it's not really about better or worse. This comparison makes it super clear. The leaky bucket is fantastic when you need a perfectly steady, predictable flow of data. But the token bucket is just way more flexible, and it's much better at handling the choppy, unpredictable nature of most internet traffic, because it allows for those controlled bursts.
Okay, so we've sorted our data, we've addressed it, we've managed the traffic flow, but there's one last piece of this entire puzzle, a layer that acts as the conductor for the whole conversation. And that is the session layer. It sits right on top of the transport layer that we've been talking about. Its job isn't moving packets around. Its job is to start, manage, and end the entire dialogue between two computers. The best way to think about it is like a phone call. The session layer is the one that first establishes the connection. It dials the number and waits for someone to answer. Then, it manages the dialogue, making sure the conversation stays active. And finally, when it's all over, it terminates the connection properly. It hangs up the phone. Without this, connections could just drop off randomly or stay open forever. It's basically the rules of etiquette for digital conversations.
So from the very second you click a link, this invisible team just springs into action. You've got the transport layer acting like the post office, and the session layer acting as the conductor. And together, they take what could be absolute chaos and transform it into the orderly, reliable internet experience that we all just take for granted every single day.
Kind of makes you wonder, doesn't it? What other unbelievably complex, invisible systems are working perfectly in the background, quietly powering all the tech we use without a second thought? It's something to chew on. Thanks for joining us for this explainer.